the previous video, we have discussed about source free RC circuit. In this video, we are going to discuss about source free RL circuit. In the last video, we mainly focused on source response, that is a circuit response, voltage across the resistor, power dissipated in the resistor, energy absorbed by the resistor, and what are the key parameters you can find from that circuit. We have mainly focused on these areas. In this video also, we are focusing on finding the circuit response, then voltage across resistor, power dissipated in the resistor, and energy absorbed by the resistor. And finally, what are the key parameters can find by using this circuit. Okay, now we will see here source free RL circuit. First we will get the doubt. Source free, without source, how it works? That is the first question we may get. That means there is no source, how it works? That is our question. Is it possible? It is possible only when we are disconnecting the source from the circuit. At that time, any one of the element can store the energy before disconnecting. What are the storing elements? We have two elements. One is the inductor, another one is capacitor. Already we have discussed in the previous video about capacitor. Similarly, here inductor is a storage element. It stores energy. Once we are disconnecting the source from this circuit, at that time the energy stored in the inductor will act, that is, will deliver. That's the reason this circuit works. Okay, let us consider a series RL circuit. It is shown in figure. This is the circuit. You can see here it is a series circuit. Already when it is series circuit, current it is same for the entire circuit. Now our main aim is to find the circuit response, that is I of t, then voltage across the resistor, power, and then energy, right? Our main goal is here to find the circuit response. Here we can take entire current, it is same entire the circuit, I of t you need to find out. Here why you are taking only inductor current? You can take any, because both the currents are same here. Why? Because of simple reason. Inductor does not allow sudden changes in the current. That's the reason we are taking here inductor current. Okay, so that is the main goal here. Our goal is to determine the circuit response, which we will assume to be the current I of t through inductor. We select the inductor current as the response in order to take advantage of the idea that inductor current cannot change instantaneously. Okay, that's the reason we are taking inductor current. At initial time, that is at t equal to 0, how much current? It is the initial current I naught. Inductor has initial current I naught. So I of t at t equal to 0, that is I of 0 equal to I naught. Okay, so inductor is having some storage capacity, right? How much storage? That is of Li square, because this inductor stores the energy in magnetic field. If it is a capacitor, it stores in electric field. So How much energy here? W of 0, because t equal to 0 here. W of 0 equal to half L into I naught square. That is the energy stored here in the inductor. Just keep in mind this one. Then apply KVL for the circuit. It is a loop circuit. So once you are applying KVL, what you will get here? Sum of the voltage, algebraic sum of the voltage equal to 0. VR plus VL equal to 0. Because there is no external source. That's the reason we are taking 0. Okay. Now we know that basic equations for the voltage across the resistor, voltage across the inductor. What is the VR? VR equal to product of current and resistor. VR equal to I into R. VL equal to L into di by dt. Right? Now substitute those values here in this expression. L into di by dt plus IR equal to 0. Already we know first order standard equations. Di by dt plus R by L into I equal to 0. That is the first order equation. Because there is no external source, that's why right hand side it is the 0. Here, this solution, we can take two methods to find this solution. Okay. One method is by using complementary function and particular integral. By using that formula we can find out. Second method, by separating the differential, that is the terms here. Suppose I is there, di by I one side, another one another side. Just separate them and find out, that is the integrate. After separating, integrate with respect to the values and find out the response. That is another way. Now we are going for second, because already we have seen by using formula in the third chapter first video, right? We are taking that. So therefore now what we are doing here, di by dt equal to minus R by L into I. Now we are taking I one side, di by I equal to minus RL by R by L into dt. That is only what we are taking here. And then integrating, rearranging the terms and integrating both sides gives this one. You see here, di by I equal to minus R by L dt. Then integrating with respect to the minimum and maximum values, lower and high value. So what is the lower value of current? I naught, initial value. High value I of t. Similarly, the time it is 0, initial time, and maximum is t. Okay, now integrate this one. Left hand side, you take first left, that is what you are getting here, di by I, integral di by I. It is nothing but ln, natural logarithmic ln. Okay, limits I naught to I of t. Right hand side, R by L is a constant, so integral dt equal to t only. Okay, so that we can see here. Ln I limits I naught to I of t. Right hand side minus R by L into t, 0 to t. Substitute these values here. You will get ln I of t minus ln I naught equal to minus RT by L plus 0. Okay. Now, you know already ln A minus ln B equal to ln A by B. Similar way, here you are also using same. Ln I of t by ln I naught. Ln I naught, that is equal to minus RT by L. That is the expression here. Now, just shift this to the right hand side, ln. If you are shifting to the right hand side, that is exponential, right? So that is only here I of t by I naught equal to e power minus RT by L. Therefore, I of t equal to I naught into e power minus RT by L. That is the expression here. You see here, this is the solution for the circuit. I of t equal to I naught into e power minus RT by L. Okay. Now, we will see the response, current response, that is I of t with respect to time. How it is? It is the exponential function, but it is the exponential decay, e power minus exponential. If current, suppose at the initial time, how much? If t equal to 0, current is I naught. That is a value. If current is approaching to high value, if you assume t equal to infinity, so how much value you will get here? That is 0. Right? E power minus infinity. That is 1 by e power infinity. 1 by infinity is 0. So if time t is approaching to infinity, current is reducing, exponential decay to the 0. Right? Now you will see that response how it is. Okay, you see the right hand side figure. So this is the graph between the current versus time. You can observe here at the initial time current is I naught. At the end you can say here t approaches to infinity, that value is 0. That is the meaning. Okay. So this shows that natural response, because source free, that's the reason it is called natural response. There is no source. Natural response of the circuit or a circuit is as an exponential decay of the initial current. Okay, so this is the circuit response. Okay, now from this equation we can find the time constant. We know the time constant, right? How much it is decaying, how much it is increasing. So in this expression, I of t equal to I naught e power minus t by tau, where tau is nothing but time constant. For the RL circuit, time constant is L by R. L by R. When time equal to tau at that time, the response I of t, right? So that value is reducing to 36.8% of initial value. You can see from this graph, at t equal to tau, at that time the response is here, this value only, 0.368 I naught. At the initial it is I naught. Okay, this much decay, exponential decay here. So this is a time constant. At this time, this is the response. That means time response is decaying 36.8% of final value. Then the time it is called time constant. Okay. So where the time constant of RL circuit is tau equal to L by R. The unit of tau, it is how much? Seconds only. It is a time only. It is a time only. Now, same equation again we are writing here. I of t equal to I naught e power minus t by tau. Now, already in the beginning we have discussed it. We need to find out voltage across the resistor, power dissipated in the resistor, energy absorbed by the resistor. First we will see those things. Already we know the expression. We found already current. If you know the current, we can find out the resistance, the voltage here, voltage across the resistance, that is from the Ohm's law V equal to IR. Similar way here, VR equal to I of t into R. That is the expression. Just substitute that VR of t equal to IR. So I expression, above expression, substitute here IR into R into e power minus t by tau. This is the voltage across the resistor. Then you take power. Power dissipated in the resistor. You know, we have three types of equations. we can find power. One is product of voltage and current. Second one is V square by R, and third one is I square by R. I square into R, sorry. I square into R. So any method you can use. I am taking here one method. First one, product of voltage and current, because both the values we know here directly. Okay. So P, that is the power dissipated in the resistor, equal to VR into I. Both the expression, product of above two expressions. You can see here I naught e power minus t by tau into I naught R into e power minus t by tau. I naught square into R into e power minus 2t by tau. This is the expression for the power dissipated in the resistor. Right? Now, how to find out energy? Energy, we know already. What is the relation between power and energy? In the first chapter itself, we have discussed all these basics, right? So, power is nothing but dW by dt. Therefore, W is nothing but integral of power into dt. That expression only we are using here. Okay, the energy absorbed by the resistor, it is, that is WR of t equal to integral 0 to t P into dt. Substitute above expression here, integral 0 to t I naught square into R into e power minus 2t by tau into dt. You can see here. Now I naught square, that is a I naught and R, both values are constants, just take it outside, and only exponential term is a time function. So integral of e power minus 2t by tau into dt. So e power minus 2t by tau by minus 2 by tau. Limit value 0 to t. Just you see here. This is the expression, right? Substitute the higher value and lower value, lower limit and higher value. Then substitute the values and also time constant tau equal to L by R. After substituting, we will get the expression WR of t equal to of Li naught square into 1 minus e power minus 2t by tau. This is the expression for the energy absorbed by the resistor. Here we can see, if t, time tends to infinity, just to observe this, t tends to infinity, what value you will get here? Of Li naught square into 1 minus, how much? It is a 0, 1 minus 0, it is a 1. Therefore, WR of t equal to of Li naught square. If the time approaches to infinity, at that time the energy stored, absorbed by the resistor is of Li naught square. That is already we know in the beginning. As time t tends to infinity, WR of infinity, it is approaching to of Li naught square. That is only value. At the inductor store the energy at the initial stage at t equal to 0. Okay, inductor store the energy at the initial, that is the initial energy stored in the inductor. Therefore, the energy initially stored in the inductor is eventually dissipated in the resistor. Okay, so at that time when t equal to 0, how much energy is storing in the inductor? At t equal to infinity, same energy is dissipated in the resistor. That is the meaning of this statement. Okay. The key to working with the source free RL circuit is mainly to find the two values. One is the initial current I of 0 through the conductor, and second one is time constant of the circuit. Okay, till now we have discussed mainly on 1 minute. Okay, so till now we have discussed mainly on response, circuit response we found, and then after that we found the voltage across the resistor, current, sorry, power dissipated in the resistor, energy absorbed by resistor. These points mainly we have discussed in this video. In the next video, mainly we are focusing on that is a RL circuit, series RL circuit, and then RC circuit, and what are the applications of these RL and RC circuits. Okay, thank you for listening. Thank you.